Alright, this is going to be a video where we're going to talk about the action potential. So the first thing to understand when we're dealing with the action potential is we want to know what it's used for. So an action potential is a very, very big change in the voltage of a membrane of a cell that's used to communicate information across long distances. And when we talk about long distances, what we basically mean is down the axon of a cell. So as you remember, we can take a look at a theoretical cell here, which has many different dendrites coming off. And then it has one big long process that extends from the back of the cell over into those little terminals that characterize the synapse. And that big long process is called the axon. And we know that the way the cell works is that it's constantly receiving information from the outside. It's constantly getting signals, these little chemical signals. And what the cell's doing at any given point in time is it's tallying the excitatory nature of those signals, and it will basically receive all of this electrical activity. And if that electrical activity, which degrades as it travels through space, summates at the axon hillock and it reaches a certain threshold, then it's going to cause an action potential, which is just going to be a very, very large depolarization in the membrane of the axon that will trigger a chain reaction and cause for there to be a signal that's basically a yes or no signal that's sent all the way down the axon and will eventually reach the axon terminal and cause the release of neurotransmitters. So what's important about an action potential is the fact that it's this very uniform mechanism. It's a very uniform signal. It's of the same height, or the same amplitude as we call it in when referring to such things. And it doesn't really add anything up together. It's just an entity onto itself. And again, all it really is the membrane getting super, super high voltage. And then when that happens, it triggers this next area. It'll become super, super high voltage. And that triggers this next area to become super, super high voltage, and so on and so forth. So the function is to basically send a binary signal. Well, not even binary. It's a one property signal, a positive electrical impulse down into the presynaptic terminal in order to release neurotransmitters. So that's the basic function of an action potential. So now we're going to go over the specifics. So when we deal with an action potential, all we have to really know about is the function of ions across the membrane. So in understanding the interaction of ions in the neuronal membrane, we need to know about two different processes. One is called diffusion, and the other one is electrostatic processes. So diffusion is a pretty simple concept. It basically states that when you're dealing with liquid or gas or anything that can shift or occupy a certain amount of space, things will move from an area of high concentration to an area of low concentration until eventually they're equal on both sides. And you could see this if you can imagine, if you had a box here and then you had, a wall that was separated into two. You had half of this was filled with water and the other half was filled with a little bit less water. And then you take this little part out. What's going to happen is the side with more water is going to flow into the side with less until you're left with a system where there's not as much as on the high side, but it's evenly distributed throughout. That's diffusion. Okay. The other thing is the electrical properties of ions. So remember when we're talking about our different players in this game, there is sodium, there's potassium, there's even calcium. But these aren't just, the elements on the periodic table. It's sodium plus. And what this is it is a cation. And you can add electrical charges or take them away by manipulating the number of electrons associated with an element. We don't really have to worry about that right now. But so this is what we call a cation. Cations have a positive charge. Potassium is also a cation. It has a positive charge. And calcium is a cation with 2 times positive charge. So all these are ions that carry a positive charge. And truth be told, you can have other ions as well that carry a negative charge, such as chlorine, but we're not going to worry about that right now, or chloride. So electrostatic forces basically refer to the fact that like charges attract and negative charges repel one another. So if you have a positive and a negative charge, they're going to be attracted to one another, and they're going to move in. They're going to want to be close to one another. Conversely, if you had 2 positive charges like this, they're going to move away from one another. And what this means is that the environment of the cell, as being positive or negative, has some electrical impact on the propensity for an ion to want to go towards it or away from it. So for instance, if we have a negative inside of a cell, negative 65 millivolts, basically the electrical forces are going to compel all of these cations to want to go in, and is going to compel all of these anions, the double negative, because this is negative and the inside of the cell is negative, those are going to want to go away from one another. So it's important that we know what diffusion and the electrostatic forces are, but all I really want you guys to realize about these two is that these two properties, these two physical properties, the chemical and the electrical properties of the interaction between the ions in the environment, are used in the calculation of something called an equilibrium potential. So all that's good and all that's perfectly fine, but basically what I'd like you all to know is that diffusion plus electricity equals the equilibrium potential. I'll just call it equilibrium potential, EQP. So, what is the equilibrium potential? The equilibrium potential is the ideal state for any ion. It is the difference between the inside and the outside of a cell that an ion wants to achieve. Now, let me go back and just backtrack a little bit to explain to you what I mean by that. When I say difference between the inside and the outside of a cell, what I mean is that, say that this is the inside of a cell, this is the outside of the cell. When you're measuring voltage, like say I was going to say that this is negative 100 millivolts, what voltage actually refers to isn't a property of the inside of the cell or a property of the outside of the cell, but a comparison between the two. So what this would be saying is if we have the inside of the cell, which is negative 100 millivolts, that is relative to the outside of the cell. And so when we say that we have something like, negative 100 millivolts or negative 50 millivolts, or if we have 20 millivolts or whatever, these are all potentials. Okay? So this is all an electrical potential. And when we refer to the equilibrium potential, we're referring to one of these numbers that a particular ion would like to get to. It would like the cell to be in such a state that the inside is negative 50 millivolts relative to the outside, or it's negative 100 millivolts relative to the outside, or it's 20 millivolts. Basically, each ion wants the inside and the outside of the cell to be in a specific way. It wants to take it to a certain potential, and that potential is the equilibrium potential. And if you understand that basic concept, then everything that's involved in an action potential makes sense. So let's just go over what so the reason that we even discuss diffusion and electrical forces is just so that we know that these two are involved in an equation that ultimately gives us the equilibrium potential. So let's talk a little bit about the equilibrium potentials of these different ions. Okay, so again, the players we have here are, we're not even going to include calcium. We're just going to have potassium and sodium. So we have potassium and sodium, and the equilibrium potential, which is calculated from the diffusion and the electrostatic forces for potassium, is negative 90 millivolts. Okay, so what that means is that if you gave potassium free range of how the cell should be, if all you had were little potassium channels in here and all of them were open, and you allowed potassium to be exactly as it wants to be, inside and outside of the cell, then the potential of this membrane would be negative 90 millivolts. That's what would happen if in potassium's ideal world. Sodium has quite a different story. Sodium's equilibrium potential is 60 millivolts. Okay, so same story. If we had nothing but sodium channels in the membrane, we'll represent these by circles so we can differentiate them from the rectangular potassium channels. Then what we would have if you just gave sodium free range to do what it wants is you'd have sodium on the inside, you'd have sodium on the outside, and the potential of the membrane here, the difference between the inside and the outside, would be positive 60 millivolts. Okay? So all you have to understand, the only thing that you have to understand for everything that's involved in an action potential is that if you give these ions the chance to do what they want, they will take the cell to they will do everything they can to take the cell to their equilibrium potentials. That's all there is to it. So if you want to understand an action potential, all you have to know is this. If you have potassium channels open, potassium is going to act. It's going to do whatever it can to get the cell to negative 90 millivolts. If you have sodium channels open, it's going to do whatever it can to get the cell to 60 millivolts. And that simple concept will allow you to understand everything that takes place over the course of the action potential. So next I'm going to explain to you the sequence of events that happens uh, over the course of the action potential, and we'll take this knowledge that we just went over here, and that will come to bear on understanding exactly what's happening on the molecular level.